Case 3, we are dealing with quadratic factors. To be more precise, so let's write here, note, more precisely, we are really dealing with non-repeated, irreducible, or prime quadratic factors. Okay, so what do we mean by that? We mean that either f of x, the rational function, which was originally p of x over q of x, or f of x after long division, we said we have a polynomial, and then the remainder divided by the denominator. So in this case, this the integrand f of x has terms in form in the following form. In this case, it will be ax plus b over ax squared plus bx plus c. Now we use the term irreducible or prime quadratic factors, and we know that we can actually factor a quadratic equation or quadratic function. So, but we can factor it only when the discriminant b squared minus 4ac is positive or 0. If the discriminant is negative, then we cannot factor, and the quadratic function is a prime or irreducible. So the condition here, where b squared minus 4ac is negative. Okay, and this is this will be helpful, because once you factor, let's say, a polynomial of a fifth degree polynomial, and you factor it as a quadratic times cubic, when cubic always can be factored. Remember, I said that last time, and if you didn't register, there is an algebra theorem that states that every polynomial with degree higher than second degree, third order or third degree polynomial or higher, can be factors as linear and or quadratic, as a product of linear and or quadratic factors. So we don't need to look for factors higher than second order than quadratic. But how do we know that a quadratic factor is prime? Well, check the discriminant. Check b squared minus 4ac. If this is negative, then you stop right there. If it's positive or 0, you need to factor it. Okay? Here's a quick example. We want to write in terms of the rational function x over x minus 2 times x squared plus 1 times x squared plus 4 as a sum of linear and quadratic factors. Well, we have the linear factor x minus 2, we have the quadratic factor x squared plus 1, and we have the quadratic factor x squared plus 4. Let's look at x squared plus 4, for example. How do we know? Well, we know that this is not factorable, but just let's test the statement b squared minus 4ac. Well, b is 0, a is 1, and c is 4. So 0 squared minus 1 minus 16 is negative 16. You can see that the discriminant is negative, therefore it's not factorable. This is a prime. Same with x squared plus 1. All right, So the answer simply will be, if I'm looking at the structure, I have something over x minus 2, and I have something over x squared plus 1, and I have something else over x squared plus 4. Okay? Over the linear factor, I'll have a over x squared plus 1. I need, instead of ax plus b, since I used a, I write bx plus c. And instead of x squared plus, instead above x squared plus 4, I'll have dx plus e, like so. Okay? So this is how you change the integrand from a rational function to a sum of a partial fraction. The next example would be example 5, where I'm talking about now where integral example, where we need to evaluate the following integral. The numerator will be 2x squared minus x plus 4. And the denominator will be x cubed plus 4x. Remember the 3 steps. The step 1 is either verify that the integrand is a proper rational function, and if not, use long division. Step 2, factor the denominator. Step 3, write the integrand as a sum of partial fractions. In this case, the integrand is a proper rational function, so we can go ahead and move on to step 2. So what do we do in step 2? Well, let's look at the integrand and write the following. 2x squared minus x plus 4 divided by x cubed plus 4x. First of all, let's factor it. Factor the denominator, step 2. So we have x times x squared plus 4. And we see that we have a linear factor and a quadratic factor. Bless you. So it will be a over x plus bx plus c over x squared plus 4. Okay? Now we need to multiply and divide by the greatest common denominator. And the greatest common denominator is simply x times x squared plus 4. And on the left side, we'll have simply the 2x squared minus x plus 4. And on the right side, a will be multiplied by x squared plus 4. And a bx plus c will be multiplied by x. Okay? And we compare now coefficients. So I need to find coefficient of x squared, coefficient of x, and the free coefficient. So remember, this is bx squared plus cx. So let's see. What are the coefficient of x squared? Then it will be a plus b. Right? Because I have bx squared. What are the coefficient of x? Only one, cx. What are the free coefficient? Only one, it will be 4a. So comparing the left side to the right side, we get the system. Go ahead, Tommy. Okay, I'm looking, first motivation. The left side has 2 as multiplying x squared, negative 1 multiplying x, and positive 4 is the free coefficient. I would need to have the same thing on the right side because this is an identity. So I'm looking for all the coefficients that multiply x squared. Well, I have a, and then bx times x is bx squared. So a plus b multiply x squared. So the coefficient of x squared is a plus b. The only coefficient that multiply x is c. and the only free term is 4a. And now I compare coefficients, and I get the following system. Compare coefficients and get a plus b equals 2, right? Now negative c equals negative 1, and then 4a equals 4. So here's a little system, but this system is really easily solvable. You can see that a equals 1, b, if a equals 1, then b equals 1 as well, right? And c already given to us is negative 1. So at this point we have the values for a, b, and c, and we can write the integral in a new, using the new form. So the integral of the rational function 2x squared minus x plus 4 over x cubed plus 4x, it now looks like the integral of a is the coefficient above x, and plus bx plus c translate to x minus 1 over x squared plus 4 dx. Okay? I'm going to break this down. And I'll write it as the integral of 1 over x dx plus the integral of x over x squared plus 4 dx minus the integral of dx over x plus x squared plus 4, like so. Again, the advantage of the fact that the integral of sum is sum of integrals, and now the integral of 1 over x is the natural log of x. We need to put it in absolute value because we don't know if x is negative or not. Now, what about the integral of x over x squared plus 4? Here we can do a mental substitution. If u equals 2x, then du equals 2x dx, and x dx equals du over 2. So after this substitution, you have du over u with the result of 1/2 du over u, and the antiderivative or the integral is natural log of u, 1/2 natural log of u. So it will have 1/2 natural log of, again, u is x squared plus 4, and x squared plus 4 is always positive, so we don't need to bother with the absolute value. Okay. Again, why 1/2? Because if we had 2x dx over x squared plus 4, then 2x dx is the u, but we don't have. We have only x dx, so we need to take 1/2. And finally, what is the integral of 1 over x squared plus 4? You should know it by now. Inverse tangent, right? So here we have the inverse tangent. But wait a second, not so fast. The inverse tangent is the integral of dx over x squared plus 1. We have x squared plus 4. So it will be 1 over 2, it will be 1/2 the inverse tangent of x over 2. And you know what? I'm going to explain this to you. Because you may not see it right away. So I'm going to explain the two integrals, this one, the second and the third one. Okay? So note here. we use the following integration. Is a question over there? Let's look at the first one, okay? Let's look at the integral. I'll call it I is the integral of x over x squared plus 4 dx. What do we do here? We let u equal x squared plus 4, right? And therefore, du equals 2x dx, and dx and x dx equals du over 2. Okay, so now I equal the integral. Instead of x dx, we have du over 2, so it will be 1/2 du over u, and the result will be 1/2 natural log of u plus a constant, or 1/2 natural log of x squared plus 4. I'm ignoring the constant because I'm going to put one big constant at the end. So this was the first integral. The second integral, j, we're going to say j is the integral of 1 over x squared plus 4 dx. Okay? I'm going to first write it as, well, no, I'll keep it like that. Here I'm going to do a little bit more work. I want to show you something that will work in general. So I'm going to say that x squared plus 4, I'll factor out the 4, and I say this is x squared over 4 plus 1. Because eventually I need 1. Okay? Furthermore, I'm going to say this is 4 times x over 2 squared plus 1, like so. Okay? And finally, I'm going to say this is equals to 4 times u squared plus 1, because I need u squared plus 1 in the denominator. So the substitution is u equal x over 2, and therefore dx, or you can see that 2 du equals dx. So I'm substituting with dx with 2 du. Okay? I'll just say 2u equals x, or 2 du equals dx. So far, so good? You follow my steps? So j, the integral, now looks like this. Instead of dx, I have 2 du, right? Instead of x squared plus 4, I have 4 times u squared plus 1. So I have 2 over 4, or 1/2, and now I have 1 over u squared plus 1 du, and this is where you see the inverse tangent. So it will be 1/2 inverse tangent of u, and or 1/2 inverse tangent of x over 2. And that's what we plugged here.